The world stands at the edge of a computing revolution, one that will redefine science, industry, security, and society. To lead this transformation, the Department of Science and Technology, Government of India has launched the National Quantum Mission, and at its heart stands the Foundation for QC Innovation, Thematic Hub of Quantum Computing, established at the Indian Institute of Science, Bengaluru. Its mission is to build scalable and indigenous quantum computing platforms, establish world-class fabrication and cryogenic infrastructure, develop a skilled quantum workforce, and accelerate translation from lab discoveries to real-world deployment. It enables national partnerships across academia, startups, industry, and global collaborators so that India becomes a global leader in quantum innovation. At its foundation are 6 national technical groups, each advancing a frontier of quantum computing. Professor Shankar Kumar Selvaraja, Project Director of the Foundation for QC Innovation, heads the national initiative to develop integrated photonic quantum processors, pushing India to the forefront of chip-scale quantum technology.
So our initiative under National Quantum Mission is going to integrate quantum emitters, quantum detectors, and the manipulating matrix all on a single platform. And ambitiously, we are going to do this at room temperature. So under Quantum Computing T-Hub, we have 6 technical groups working on 4 technology verticals. So all these technologies are seen as potential platforms to do quantum computing with different level of maturity. This is a unique initiative from NQM where we are equally investing in all these potential technology platforms, which is unprecedented in world scenario.
At TIFR Mumbai, Dr. Rajmani Vijay Raghavan leads the advancement of superconducting qubit technologies, a globally recognized pathway toward fault-tolerant quantum computation.
At the Quantum Measurement and Control Laboratory at TIFR, we work with superconducting circuits. These are circuits that are patterned on small chips, and these are macroscopic in size, but they actually act like artificial atoms. So that's the basic architecture that we work with. This field is about 30-35 years old, but has gained a lot of momentum in the last few years. And this lab is going to be part of the National Quantum Mission. In the National Quantum Mission, we hope in the span of the next 3 years or so to build quantum processors with about 24 qubits. But over a slightly longer term, maybe in the next 5 years or so, we hope to be able to build a processor with 100 qubits. And in that, we will also have indigenous fabrication facilities, indigenous development of electronics, and almost everything else should also be done in-house by then.
The team led by Professor Abhishek Deekshit of IIT Delhi is designing and demonstrating scalable semiconductor qubit quantum processors, laying the groundwork for indigenous quantum chip manufacturing in India. At the Raman Research Institute, Professor Saptarshi Chaudhary leads efforts to advance neutral atom and trapped ion platforms, enabling high-fidelity quantum control and modular systems.
Atoms are ions at the fundamental building blocks of matter. We harness the quantum properties of trapped atoms and ions for developing the futuristic quantum computing technologies. Over the past 1 year, with the support of Department of Science and Technology and the Mission Coordination Cell, we are in the process of deploying usable technology for developing the quantum computing platforms using neutral atoms and trapped ions. And neutral atoms and trapped ions-based quantum computing offers certain benefits which complements the other platforms. For example, there is an idea of analog quantum computing where neutral atoms can be best used for developing certain quantum simulation protocols where there can be advantage in utilizing this particular platform.
At the Indian Institute of Science, Bengaluru, Professor Chandrasekhar Sinemd is developing programmable photonic architectures, using light itself as a secure and scalable quantum resource.
So our research group is working on photonic quantum computers. From last few years, we have developed a novel scheme for realizing quantum computers using photons' different degrees of freedom. And that has now been translated into an experimental setup for the last 1 year. To begin with, we started the 2-qubit setup where the 2 qubits was generated using photons, and that 2 qubits was used to have to build a quantum random number generator. So that quantum random number generator has a cybersecurity applications. So after that, we have built a 4-qubit setup where we could generate a public and private key, which again has a cybersecurity applications. The sidewise, we also had a 3-qubit setup, which was used for realizing quantum teleportations. This kind of sets grounds for us to build a number of qubits and control them. So now we have a 6-qubit setup in our lab, from which we have built a 6-qubit entangled state, which can be controlled according to our wish. So though realizing gates is our larger number of gates is a target to scale it up to more number of qubits and implement algorithms, the work is in progress to scale it up within coming months. So this sets us a ground to build up to 20 to 40 qubits in immediate 1 to 2 years time. And the scheme will then be ready to be translated into photonic integrated circuit, where we can translate whole the scheme into a compact system where larger hundreds of qubits can be realized, and one can realize a practically usable photonic computers.
And at IIT Bombay, Professor Suddhasatta Mahapatra and his team are working toward a 50-qubit silicon spin-based quantum processor, a major step in semiconductor-driven quantum scaling. As India strides forward into the quantum age, the Foundation for QC Innovation stands as the cornerstone of that journey, with alignment across national labs, academic institutions, startups and industry, across 6 technology frontiers. They are building not just quantum computers, but the future of innovation. They are shaping a world-class quantum ecosystem, one that empowers researchers, fuels startups, nurtures talent, and secures India's technological sovereignty. Because the quantum revolution is not coming, it's already beginning, and India is leading it.